It is late. You are probably staring at a glowing IDE right now, hunting down a logic bug in some messy codebase. Or maybe you're just unwinding after a long, brutal sprint, just watching the cursor blink on a blank screen. It's quiet.
Yeah, that late-night coding silence.
Exactly. And in that quiet, I want you to imagine playing the absolute simplest child's game in the world. Someone gives you the first half of a sentence and you just instinctively guess the next word. Like, the cat sat on the...
It's pure reflex.
Right, it is. But now, take that deceptively simple, almost thoughtless game and scale it up. Imagine playing it billions of times, iterating across, well, every published book, every open source GitHub repository, every deeply nested forum argument.
Every piece of text humanity has ever bothered to digitize, basically.
Yeah, that right there. That massive brute force guessing game is the pulse of the most disruptive technology in modern software engineering.
It is the underlying engine running beneath GPT. Generative pre-trained transformer.
And that is our mission for tonight's deep dive. We are unpacking a massive stack of architectural notes, research papers, and historical data on GPT. We really want to tear this system down to the bare metal, look at the architecture, and understand how this seemingly basic concept of next token prediction just completely rewired the landscape of computer science and your day-to-day life as a developer.
Yeah, and it makes sense to dissect that acronym right up front, I think.
Yeah.
Because the naming convention itself is, well, it's a literal map of its architecture. Generative means it produces text sequentially, strictly word by word.
Right.
Pre-trained indicates that it learns broad, foundational language patterns from a massive, unsupervised data set, before it's ever fine-tuned for a specific task. And transformer is the underlying neural network architecture doing the heavy lifting.
To really grasp how this guessing game changed everything, we have to look at the massive architectural gamble the creators made. I've been looking through these system design notes, and they didn't just build a new model. They looked at the standard playbook for natural language processing and essentially threw half of it in the trash.
They absolutely did. I mean, if you look at earlier, highly successful transformer models, like Google's BERT, they operated heavily on what we call an encoder architecture. BERT was it was a reader.
It read the whole thing at once.
Exactly. It would ingest an entire passage of text into memory all at once. It analyzed words contextually from both the left and the right simultaneously. It possessed this bidirectional understanding.
Which makes it great for certain things.
Right. Brilliant for classification, sentiment analysis, categorization. But it turns out it is surprisingly terrible at actually generating natural flowing text.
Right, because parsing an entire document to extract meaning and streaming out a brand new document from scratch are two fundamentally different computational tasks. So the creators of GPT looked at the original Transformer paper, which featured both an encoder block to read and a decoder block to write, and they made this radical bet. They stripped out the encoder entirely. They bet the entire house on the decoder, just the writer.
Yeah, and the mechanics of that decoder-only architecture they're beautiful in their systemic purity. When you pass a string into this system, say a prompt like, the weather in Dublin is usually, it doesn't parse it as a sequence of human letters, it tokenizes it.
Okay, let's unpack this. Because my notes highlight tokenization, but for a developer used to parking strings, tokens in this context aren't just whole words, right?
Precisely. The model uses a fixed vocabulary, usually around 50,000 to 100,000 tokens. A very common word like the is mapped to a single integer token, but a word like usually might be split into two subword tokens, like usu and ally.
So it's a compression mechanism.
Yeah, exactly. These integer tokens are then mapped into embeddings, which are high-dimensional vectors.
So we are taking a discrete piece of text and turning it into an array of floating point numbers. How does that actually capture meaning, though?
Think of it as mapping words into a massive multidimensional geometric space. Like, in a 10,000-dimensional space, the vector for dog and the vector for puppy are physically plotted very close to each other, while the vector for refrigerator is miles away.
Okay, that makes sense.
The embedding captures the mathematical relational meaning of that chunk of text based on how it was used in the training data.
But a bag of floating point numbers isn't a coherent sentence. I mean, in programming, syntax is everything. The bug caused the crash is a fundamentally different system state than the crash caused the bug. The words are identical, but the order changes the entire reality.
Which is why the architecture immediately injects positional encoding into those embeddings. It literally adds a mathematical wave function to the vectors to stamp them with their sequential order. From there, these position stamp vectors are pushed up through a towering stack of transformer layers. And this is where the real computation happens. Each layer consists of masked self-attention mechanisms and feed-forward networks.
Let's drill into the self-attention part because the math here is fascinating. For an engineer listening, how should we conceptualize attention?
What's fascinating here is that you can think of self-attention as a fuzzy, differentiable key value store.
Oh, I like that analogy.
Yeah, for every token, the network generates three vectors: a query, a key, and a value. So the word Dublin might send out a query vector that mathematically aligns with the key vector of the word weather earlier in the sentence.
And then it calculates the relationship.
Right. By calculating the dot product of those vectors, the system generates attention weights. It dictates exactly how much focus Dublin should put on weather to understand its current context. The feed-forward network then processes those weighted relationships through nonlinear transformations, passing the refined context up to the next layer.
I see that mechanism, but this brings me to a huge point of confusion I had when reviewing the architecture. You mentioned masked self-attention, the causal mask, the autoregressive property. Looking at this from a system design perspective, I see a massive, glaring bottleneck here.
The left-to-right constraint.
Exactly. The mask physically prevents the attention mechanism from ever peeking ahead at future tokens. It can only ever look backwards. If it can only read strictly left to right, isn't it essentially coding blind? Like, how can it possibly formulate a cohesive response to a complex architectural query if it can't see the end of its own sentence before it starts generating the reply?
That is the defining paradox of GPT. That exact limitation, this forced mathematical blindness to the future, is the very thing that gives the model its generative power.
Really?
Yeah. Because it is mathematically constrained to predict the next token based only on the sequence that came before it, it has no choice but to become the ultimate natural language generator. It isn't trying to solve an entire logical puzzle all at once. It is strictly predicting the next state.
Just one token at a time?
Exactly. You ask it for a token, it outputs a probability distribution, and it selects one token. You append that new token to your input, run the entire sequence through the massive stack of layers all over again, and ask for the next one. The constraint forces the generation.
It's an infinite loop of streaming output, just a continuous while loop of next token prediction. But that brings up a logical gap that I think any engineer listening will immediately spot. If the architecture is just a blind left-to-right token generator, it shouldn't be able to perform complex cognitive tasks. I mean, a fancy multi-dimensional autocomplete doesn't write functioning Python scripts. And it certainly doesn't debug Kubernetes deployment logs.
You are absolutely right, it doesn't, not inherently. Until you introduce the variable that completely shattered the established rules of software engineering. Brute force scale.
Right. So GPT-1 proved the chef could learn basic knife skills. But as an engineer, your next question immediately becomes, what happens if we give that chef 1,000,000 times more ingredients, 1,000 more ovens, and exponentially more heat? Does the kitchen burn down, or do we get a Michelin star? That exact engineering question led to the scaling hypothesis.
Exactly. And let's look at how that actually played out. In 2018, GPT-1 had 117 million parameters and was trained on a few thousand unpublished books. It proved that unsupervised pre-training worked.
That's where the culinary analogy from the notes comes in.
Yeah, it's a great analogy. Instead of training a different chef from scratch for every single highly specific dish you want to serve, you send one chef to master broad, fundamental culinary physics: heat management, knife skills, flavor profiling.
Basics.
Right. Once they have that general foundation from raw text, you can teach them to specialize in pastry or sushi incredibly fast.
But the kitchen didn't burn down when they scaled it. It thrived. They scaled it up 13 times larger for GPT-2, 1.5 billion parameters, trained on millions of web pages curated from outbound Reddit links. And suddenly, this left-to-right autocomplete is writing incredibly convincing, multi-paragraph fake news articles about scientists discovering unicorns in the Andes.
It was wild to see.
And it's doing something researchers call zero-shot learning. It is summarizing text and translating languages without ever being explicitly fine-tuned or programmed to do so. You just type translate English to French, hey, cheese equals, and the model, just by predicting the most statistically likely next token, outputs fromage. And this is the era where OpenAI famously declared the model was too dangerous to release.
Yes, they held back the full 1.5 billion parameter model for months. They released only smaller, nerfed versions to the public first. It ignited a massive industry debate about responsible disclosure and AI safety. Many wondered if it was a genuine precaution or just a brilliant marketing stunt to hype the technology.
I have to push back on that controversy, looking at it through the lens of traditional system architecture. Was the model actually too dangerous at a mere 1.5 billion parameters? Or were developers and researchers just deeply, fundamentally freaked out by the implications of the scaling hypothesis? Think about it. In traditional software engineering, scaling up a system inevitably breaks it. The core logic that builds a sturdy wooden bridge over a small creek fundamentally fails if you try to stretch that exact same design over a mile-wide bay. You need a completely new design, new physics, new materials. But here, the same basic left-to-right recipe just kept getting better the bigger they made it.
Your intuition is spot on. The underlying fear wasn't just about what GPT-2 could do at that moment. It was the terrifying realization of the scaling laws it validated. The decoder-only architecture won specifically because of its remarkably clean scalability. It has one job, one objective function.
No complex balancing act.
None. You don't have to balance a complex encoder against a complex decoder. You literally just stack more transformer layers, widen the dimensional network, and feed it exponentially more data and compute. The math doesn't change, only the volume.
Which perfectly explains the paradigm shift of GPT-3. They pushed the volume to a staggering 175 billion parameters, over 100 times larger than GPT-2. And that leap absolutely demolished the traditional machine learning workflow.
It really did. Prior to this, if an engineering team wanted an AI to do something new, the workflow was grueling and highly specialized. You had to collect a massive labeled data set, painstakingly fine-tune the model weights, evaluate the output, iterate, and retrain. GPT-3 bypassed all of that by introducing reliable few-shot learning.
Right, no architectural retraining required. You don't alter the underlying weights of the model. You just show it pattern directly in the prompt. You type Titanic, ship iceberg, the Matrix, pill computer, the Lion King, and it instantly spits out a lion and a crown emoji. It uses the examples in the prompt as temporary in-context programming. It alters its attention matrix on the fly based purely on the context window.
And beyond few-shot learning, the sheer scale of 175 billion parameters unlocked what researchers call emergent abilities.
This is the crazy part.
Yeah, behaviors that were never explicitly programmed and that simply did not exist in smaller parameter models suddenly materialized out of nowhere. It could perform multi-digit arithmetic, it could write functional React components, it could generate valid, highly complex SQL queries.
How does that happen, though? I mean, how does next token prediction suddenly learn SQL?
Because the training data includes the entire internet. It ingested millions of Stack Overflow threads where human engineers posted a natural language problem, followed by a block of code, followed by an explanation of the syntax. By learning to predict the next token across that massive corpus, the model internalized the deeply structured logical syntax of programming languages. The ability to code wasn't the training objective. It emerged purely from the pressure of predicting the next token across a mathematically structured data set.
The scale proved the science. But the way this was actually delivered to you, the developer listening right now, is what truly revolutionized the industry. Because OpenAI didn't package up GPT-3's 175 billion parameters, zip up the weights, and drop them on a GitHub repo for you to run locally.
No, they didn't. They kept the model entirely behind their own firewalls and released an API endpoint.
Here's where it gets really interesting. This was the ultimate abstraction layer. You no longer needed a dedicated machine learning operations team. You didn't need to provision and rack wildly expensive GPU clusters. You didn't need to worry about gradient descent or optimizing tensor memory. It is exactly like the shift from managing on-premise, bare metal servers to deploying serverless cloud functions. Just as software engineers stopped caring about the physical hardware and just integrated with an AWS endpoint, developers stopped trying to train their own bespoke language models and just plugged into the GPT API as a microservice.
And that single abstraction layer created an entirely new engineering discipline, prompt engineering. Developers stopped writing imperative code to dictate strict system behavior, and they started writing natural language.
Right, it became the new syntax.
Yeah, you would pass a string saying, "You are a highly analytical code reviewer. Find the security flaws in the following Python function and output your findings as a JSON object." Natural language became the ultimate universal programming interface. Thousands of startups, automated code review tools, IDE assistants, dynamic customer service agents, they bloomed practically overnight, all built by simply routing data through this single API grid.
But as developers built these massive, complex ecosystems on top of this API grid, relying on it for mission-critical logic, they inevitably slammed into a very hard wall. because the core architectural bet we talked about at the beginning, that left-to-right decoder-only generation, carries a permanent structural flaw.
Yes, in the literature, it is known as the autoregressive curse, because the model generates text strictly one token at a time, moving irrevocably forward through the sequence. It can never go back and revise an earlier token based on a realization it has later in the output.
It's like being forced to write a highly complex technical design document, but your keyboard physically does not have a backspace key. Every single keystroke you make is permanent. If you start a sentence and realize halfway through that your core premise is logically flawed, you cannot delete the beginning. You just have to desperately try to salvage the ending to make the whole thing sound coherent.
Which highlights a critical reality for developers to understand when integrating these models into their stacks. GPT's reasoning is fundamentally alien to human reasoning. When a human engineer solves a math problem or debugs a script, we think, we reconsider, we scratch things out, we revise our mental model, we back up.
We iterate in our heads.
Exactly. GPT commits to every single token irrevocably. It builds on its own output context, even if that previous output was a total hallucination or a glaring logical error.
So, what does this all mean for how we use it day to day? The notes we pulled use this brilliant jazz analogy that I think perfectly captures the reality. When you watch an AI reason its way through a complex logic puzzle in your terminal, it is not actually thinking like a mathematician. It is improvising a jazz solo. Every single note follows the last note perfectly based on statistical probability. But if it accidentally plays a discordant wrong note, say, it hallucinates a totally fake React library, it can't unplay it, it can't backspace. It just has to keep playing and spend the next 20 lines of code confidently pretending that fake library is a standard dependency, trying to make the wrong note sound like intentional jazz.
That is exactly what is happening mathematically under the hood.
Mm-hmm.
The hallucinated token becomes part of the permanent context window, and the model must predict the next token based on that newly flawed reality. Now, developers have engineered highly clever programmatic workarounds for this curse. Chain of thought prompting is a major one.
That's where you append think step by step to the prompt, right?
Exactly. By instructing the model to think out loud before outputting the final answer or the final code block, you force it to generate intermediate reasoning tokens. Because it's an autoregressive model, generating those intermediate steps provides vital, accurate context into its own attention window for the later tokens, significantly increasing the probability that the final solo stays on key.
Oh, that makes perfect sense.
Another common programmatic workaround is self-consistency, where developers run the exact same prompt through the API 10 different times and write a script to take a mathematical majority vote of the outputs, filtering out the anomalous jazz solos.
I mean, these are still just patches. Chain of thought, self-consistency, complex, agentic prompt engineering frameworks. They are incredibly sophisticated duct tape placed over a foundational architectural constraint.
If we connect this to the bigger picture, the autoregressive curse remains the fundamental ceiling of current decoder-only models. It's the unavoidable tax paid for the infinite scalability of left-to-right generation.
Right. The elegant, stripped-down architecture that allowed it to cleanly scale to 175 billion parameters, process the entire internet, and change the software industry is the exact same architecture that fundamentally prevents it from ever hitting backspace.
It's an incredible journey when you step back and look at the whole system design. A deceptively simple idea, a decoder-only transformer, forced to predict the next word, combined with relentless, rule-breaking scaling, and finally abstracted away behind a simple API endpoint.
It created a completely new era of software engineering. It turned natural language into executable code, even while dragging along the heavy, irreversible limitations of its autoregressive design.
It proved to the entire computer science field that an almost absurdly simple objective function, when pushed to its absolute computational limit, can mimic profound multidisciplinary understanding.
Which leaves us with a fascinating, maybe slightly unsettling thought to chew on as you switch tabs and get back to your code. We just spent all this time technically critiquing GPT for its autoregressive curse, for generating text irrevocably, improvising one single token at a time without the ability to look ahead, just playing a continuous jazz solo of words. But how often do we humans actually do the exact same thing in casual conversation?
Oh, wow.
Think about it. You start a sentence in a stand-up meeting without having any real idea how you're going to finish it. You're just improvising word by word, hoping your syntax lands gracefully. Is our own daily conversational intelligence just a biological version of next token prediction running on wetware?
Now, that is a profound architectural question to end on.
Keep that in mind next time you are talking your way through a messy pull request. Thank you for joining us on tonight's deep dive. Keep building, keep questioning the architecture, and we'll catch you on the next one. The cat sat on the rest. Good night.
Yeah.